right. Let's get started. The first thing I wanted to mention is, again, we've got our midterm on October 11th. If you had an accommodation for extra time or a non-distraction environment, I sent an email this morning to set up either for you to come early to start, since I have the same class back-to-back, or to set something up with class. If you didn't get an email from me, and you should have, send me an email, because it just means that I missed the accommodation when I was going through the list. And so today's lecture is going to complete the content on simple linear regression. So after today, you will know all there is to know. Well, not quite, but you'll know all the things that you'll need, at least for the midterm, on the topic. And if we have enough time after doing the content for today, I'm going to try to go through basically a whole game where I go kind of from start to finish analyzing a data set, so you can sort of see how all of this flows together. So I think hopefully that will help, because sometimes it can be hard to put all the pieces together when we're sort of doing it in little increments. And so I'll start that at the end of class, and as we have time, if I have time, I'll finish it, and if not, we'll start up on Tuesday, finishing that up. And then Tuesday you have a lab, and then Thursday we'll do a review for the midterm, and then the midterm will be on the following Tuesday. And so that midterm, I think I mentioned this last time, but the midterm is going to be held in class, but it'll be on Canvas, so you'll be able to do it on your computer. If you would prefer to have like a physical copy, just let me know, and I'm happy to give you one on paper as well. The reason it's on Canvas, some people had an accommodation that they needed to take exams with like technology, and so I just wanted to make sure that it was sort of fair for everybody in that regard, and also so that you can access your notes and slides and things like that. So it will be open, everything, but with the exception of like other people. So you don't like text your friends during the exam, but you can look at the slides and things like that. It is timed, so it is just during class, or if you had extra time, a little extra time. So I would suggest that you make like a cheat sheet or something to quickly look up information that you're going to need, because if you're going to have to search through every single slide deck, that will be time consuming and might take up too much of your time. So, but we'll go over some of that in the review as well. The content, it won't be anything where you have to actually program in R, but it might be that I give you some R output and ask you to pull out information from it and explain what it means. Or it might be that I give you some incomplete R output and you would need to kind of fill it in with the other pieces. So for example, those Anova tables we did last time, some of the information in the tables is redundant. So like, for example, you could get the F statistic by taking the ratio of the mean squared error, or the mean squared model and mean squared error. Or like in the summary from a linear model, you can get the T statistics by taking the ratio of the estimates and the standard errors. So I might leave off parts and ask you to fill them in, so that might be part of the exam. Or I might show you some R code and ask you like what type of plot that R code generates. But you won't have to actually put anything into R during the exam. It can all just be done within Canvas. Are there any questions about that? All right. All right, so we're going to start by drawing the connection, and we drew the connection a little bit with correlation in this last lab that you did. We're going to talk about another measure called R squared, which is basically a way to summarize how well your model fits your data, and it ties in really nicely with the different portions of variability that we talked about earlier. But before we do that, let's go ahead and copy this new template into RStudio Pro. Go ahead and load the packages at the top. We're going to be using the Porsche price data again. So take a look at that to remind yourself what the variable names are. And then fit a linear model predicting the price of the Porsche from the mileage, the miles that have been driven. And then I want you to examine that Anova table that we talked about last time. See if you can pull out the F statistic and the associated p-value. And this should say what hypothesis is it testing? See if you can establish what hypothesis that p-value is testing. I'll give you a couple minutes to work on that, and then we will do it together. right, I'm going to go ahead and load these packages as well as the data frame. Oh, and one thing I wanted to mention here, it's important when you're, the couple things that I always like to do when I'm working in these QMD files, first I like to check this render on save button, so every time I save it, it will render. And the other thing I like to do is render these documents all the time. Like pretty much every time I finish up with one of these code chunks, I like to render them. And that's for two reasons. One, when you click the render button, it automatically saves it, which is important because this RStudio Pro session is run in the cloud. So if you leave your documents unsaved, they can sometimes disappear. So you want to make sure you're rendering them frequently so that doesn't happen. And the other reason I like to render frequently is it makes it easier to figure out where there's a mistake in my code. So if you wait a really long time before you try to render your document, then it can be harder to trace back where the mistake is, versus if I render every single time after I create a new R chunk, I can kind of narrow down that the mistake is in that R chunk if it doesn't knit or if it doesn't render one time. Okay, so I've loaded my Porsche price data, and I can see it's up here in my environment. I could click on it to see that it has 3 columns, price, age, and mileage. It has 30 observations, which I can see from looking at the information in this environment, or I could just scroll down and see the bottom of the data, the 30th observation. Or I can, down here in the console, do question mark Porsche price to be able to look at the help file for this particular data set, which lets me know that this is a data set with 30 observations and 3 variables, price, age, and mileage. All right, if I wanted to fit a linear model to predict the price from the mileage, what would I do? LM, price, mileage. Data is Porsche price. All right, and if I wanted to save that as an object so I could use some other functions on it, what would I do? Yeah, I could assign it to some object called mod. All right, so I'm going to go ahead and render that document. Now, when I do this, when I have assigned it like this, if I look at my rendered document, you can see the code, but you don't actually see the output from the model. If I wanted the output to print in my document, what would I need to do so that I could see it? Yeah, I need to type mod, or I could write summary mod, since that would have the same information with actually a little bit more. So that's usually what I like to do. So I'm going to go ahead and do that as well. All right, so now I can see this output. Now I had asked you about the F statistic and the p-value for the F statistic, which you can get using the Anova function, but you can also get it just from the summary. And so looking at this output, what is the F statistic for this data? .3, exactly. Now, if I didn't have any of this printed on the bottom, how could is there a way for me to get this number from just the values in this table? Are any of these related to that number in the case of simple linear regression? So this was like at the very end of lecture last time, but it turns out in the case of a simple linear regression model where you just have one variable, the t statistic, if you square it, is exactly equal to the f statistic. And so if we took this negative 10.4 squared, that would be equal to 108. And so if I, for example, gave you just this top part and had like blacked out this bottom part, you could get that f statistic by just squaring this t statistic. And similarly, the p-value for the t statistic here is exactly equal to the p-value for the f statistic. Why are those two p-values equal? What is it? Yeah, so it turns out that the null hypothesis, or the hypothesis that's being tested by this statistic, or by this p-value, is exactly the same as the hypothesis that's being tested by this p-value. So this one up here, what hypothesis is being tested for this t statistic? What are we testing for this p-value? What's the null hypothesis? Beta 1 is equal to 0, yeah, and the alternative is that it's not equal to 0. What's the null hypothesis down here for this F statistic p-value? So the F test is testing the difference between the model that you have created and the intercept-only model. So what the null is that the model that you fit here with beta 0 and beta 1 is equal to a model with just beta 0. And so in the case of simple linear regression, that's the exact same null hypothesis. It's the same as saying that beta 1 is equal to 0, because if beta 0 plus beta 1 equals beta 0, the only way for that to be true is if beta 0 is equal to 0. So it's the same null and the same alternative, which is why the p-value ends up being exactly the same. So this is only true for simple linear regression where you just have one variable, but it's worth noting since it sort of helps describe the relationship between these two pieces. All right, and the other thing, if this p-value here, so this p-value, what is that telling us? What's that probability telling us? Yes, given the null hypothesis is true. Exactly. So the probability that that we'd see an F statistic bigger than 108.3 or 108.3 or bigger, given that the null hypothesis is true. So given that the true beta 1 coefficient is 0, it's this very, very small number, this basically 0. If we were to try to generate the distribution of the F statistic under the null, it would have we'd need 2 degrees of freedom to do that. What are the 2 degrees of freedom we would use to do that? What is it? Yes, 1 in 28, exactly. So the 1 corresponds to the model degrees of freedom, and the 28 corresponds to the degrees of freedom of the error, or the residuals. So this is equal to the number of variables in your model, which in simple linear regression is just 1, and this is equal to n minus 2, and so in this case there are 30 observations, and so it would be 28. All right, let's use the Anova function to see what we get from that. So when I use the Anova function, I get this little table. It also has the F value as well as that P value. What is my sum of squares for my model? Yep, exactly, 5,565.7. And what about my sum of squared error? Exactly, 1,439.6. And if I wanted to get my sum of squared total, how could I get that from these numbers? You could add them, exactly. If I add these two numbers together, that would give me my sum of squared total. Now, if I didn't have this column here with this F value, how could I get that 108.25 using just the information in these first columns here? How do I calculate the F statistic?
Is that QF?
You could get the p-value from PF, and you could back calculate to QF with that is true. I also could get it just from these two. It's the mean squared error divided by the sum of squared error is going to be equal to that F statistic. So I could take this 5,565.7 and divide by 51.4, and that would give me that 108.25 as well. All right. Great. So, partitioning variability. We talked about last time how we can partition the total variability in our outcome or our response. And so like in the case that we just did in that Porsche price, and that's going to be equal to the amount of variability that's explained by the model plus the amount of variability that's unexplained, or the variation in the residuals. And so that's because we can show this mathematically. Basically, if we take, so y minus y bar here, this is like the observed y minus the average y, is going to be equal to y hat minus y bar plus y minus y hat. All I've done here is I've basically added 0 to this equation because I've added y hat minus y hat. So y hat minus y hat is just 0, and I end up with this y hat over here and this y hat over here. So this is just true by default. I can add these sums and these squares to each of these, and the same mathematics holds. And each of these are the sum of squared total, the sum of squared model, and the sum of squared error. So this is why this is able to work. And we can use these quantities for different things. So we knew if we divided these by their degrees of freedom, we end up with that mean squared model and the mean squared error, which we can use to get the F statistic. And there's another statistic that's quite helpful called the coefficient of determination. This is often referred to as R squared. It's the fraction of response variability that is explained by the model. So it's the amount of variability explained by the model divided by the total amount of variability. So based on those sum of squares that we just talked about, what do you think this fraction is here, if it's going to be the amount explained by the model, the proportion explained by the model? So what do you think the numerator would be if the numerator is trying to describe the variability in the model? Sum of squares. Yeah, exactly, the sum of squares model. And then what do you think the denominator would be if it was describing the total variability? Sum of squares total, exactly. So we can take basically this coefficient of variability, or coefficient of determination, or R squared. It's just the variability explained by the model divided by the total variability in Y. So just the sum of squared model divided by the sum of squared total. So if we have this sum of squared model and sum of squared total, how do you think you could calculate R squared if instead of having the sum of squared model and sum of squared total, all you had was the sum of squared total and sum of squared error? You can take like a minute maybe to try to see if you can derive that, just to see how this is related to the sum of squared error as well. So basically, if you didn't know what the sum of squared model is, you only knew what the sum of squared total and sum of squared error was, how could you calculate R squared from that? Anybody get how you could do that? Exactly, because we know that the sum of squared model is just equal to the sum of squared total minus the sum of squared error. You could use the sum of squared total minus the sum of squared error to get that r squared value. If you divide each of these pieces by the sum of squared total, that will be the same as 1 minus the sum of squared error over the sum of squared total. So each of these equalities, I think they kind of make sense because basically this first one, basically we're just saying it's the proportion explained by the model, which is going to be equal to 1 minus the proportion not explained by the model. So these sort of give the same result, and I think it's kind of an intuitive result. And this is a really useful metric because it can help you assess how well your model fits, or basically how useful the variables in your model are for explaining the thing that you're trying to explain. So we can do this in R. Here I'm predicting, this is using that Magnolia data, I'm predicting the leaf length from the leaf width of some magnolia leaves. I've got 100 in this particular sample. When I look at the output here, I get this r squared value of 7.5%, which lets me know that 7.5% of the variation in the length of a magnolia leaf is explained by its width. Okay, so go back to that application exercise and run the summary function on your model, predicting Porsche price per mileage, and get the r squared and see if you can see how to interpret it. And then I want you to also run the Anova function and see if you can calculate by hand and get that same r squared value. I'll give you a couple minutes to do that, and then we will do it together. All right, so looking at this output, what is the r squared value for this model? It's the multiple. 0.7945, exactly. And how would you interpret that in the context of this model?
The percentage of variation in price that is explained by variation in mileage.
Exactly. The percent of variation in price that's explained by mileage is about 80%. So about 80% of the variability in the price is explained by the miles driven. So that's pretty good. This is a pretty good model that suggests that a lot of the variability in our outcome is explained by the predictor that we've chosen. So R squared, yes?
What is adjusted R-squared?
So adjusted R-squared, we'll cover this more when we get to multiple regression. What this does is it slightly adjusts for the number of variables that you have included in your model. So it turns out that based on just the mechanics, like this, the way that R-squared is calculated is the sum of squared model divided by the sum of squared total. When you add new variables, it necessarily is always going to be a little higher. So basically, it's not penalized for the number of variables you add. So when you're trying to use R-squared is a nice way to sort of give you a sense for how well the model is able to estimate the thing you're trying to estimate. But if you're trying to compare two models and you're trying to decide which model to use, if you had a model that had 10 variables and a model that had 9 variables, the R-squared value will always be higher in the one with 10 versus 9, whereas the R-squared adjusted has a little penalty for the number of variables that you include. And so basically, it is a little bit a better tool if you're trying to compare two models with a different number of variables to help you decide which model is better. So the statistic that we just talked about is this one right here. This basically just has a little penalty term, which we will talk about that once we get to multiple regression. Okay, so we've got this 80% of variability is explained by the model. If I just had the output from this Anova table, how could I calculate that R-squared value? Exactly, I could divide the SS model over the SS total, which in this case, would be, here I could take, this is that SS model, and then the SS total is going to be equal to that SS model plus the sum of squared error. So if I do that, I end up with 0.7945, which is exactly the same as what I got when I looked at the summary. All right. All right. So that is a little bit about R-squared. R-squared is a nice metric because it basically gives you a sense for how well your model fits. The F statistic also can give you a sense for how well your model fits compared to an intercept-only model. But one downside of the F statistic is that as you add more observations, you can get closer and closer on the absolute scale to the null while still being statistically significant because that is it's this as well as this t-value. They're driven by the standard error, which is equal to the standard deviation divided by the square root of the sample size. So as your sample size grows, you can detect smaller and smaller differences. And so using these p-values alone can be a little bit misleading if you're trying to decide whether a model fits the data well, because they can just be driven by a very large sample size as opposed to a good model fit. So the R-squared is sort of nice because it's agnostic to that. It doesn't matter how many observations you have. It's just telling you the proportion that of the variability that is explained by the model. All right, so we're going to change gears a little bit and talk about prediction intervals, which is a different type of uncertainty that you might be interested in when doing a regression analysis. So far we've talked about confidence intervals for our parameters. So if our interest was inference, that is, if we were interested in describing the relationship between x and y, and we wanted to do so via a simple linear regression model, we would fit our model. We would be estimating the slope here, which is an estimate of the true beta 1 parameter, and we could use these confidence intervals, which basically would allow us to have some sense of how often the intervals that we would be calculating if we were to use the same sampling method many times and compute intervals on each of them, how many of those intervals we'd expect to contain the true population parameter, which often is 95% if we're doing 95% confidence intervals. So we've talked about these confidence intervals for the slope, which would be basically that beta hat 1 value. And so that confidence interval is going to be beta hat 1 plus this critical t value. So this is that value from the t distribution times the standard error of beta hat 1. And so in R, we could do this using the conf_int function. So for example, here, if I'm looking at the relationship between leaf length and leaf width, and I'm interested in quantifying that relationship, I could estimate that beta hat 1 as 0.4386. And then I could run the conf_int function on that model to get a confidence interval for that. And so for this beta hat 1, what is my confidence interval for this model, for that beta hat 1 value? Exactly, 0.13 to 0.747. And so if I wanted to calculate this by hand without using the conf_int function, I could use this beta hat 1 as that'll be the center of my interval. And then if I want the lower bound, I would subtract that critical t-value times this 0.1552, the standard error. And for the upper bound, I would add the critical value times that standard error. And so this is how I could do this by hand in R instead of using the conf_int function. I can get those critical t-values by using that qt function to pull out the quantile from the t-distribution that corresponds to the probability that I'm interested in. And here the degrees of freedom is going to be equal to the number of rows in my data minus 2. Both of these t-star values will give you the same answer. In the top one, I said I wanted the 2.5th percentile, and so I used this lower tail equals false. Or in the bottom one, I said I wanted the 97.5th percentile, and so I didn't need to use that lower tail. These will give me the same answer. Why am I using 0.025 and 9.75 instead of 5 and 95, since I'm calculating a 95% confidence interval? Exactly, I want just 2.5 on each side, so I don't want, if I did 5%, it would be too wide. It would be like a 90% confidence interval. So I just want, as a two-sided interval, I want that t-star to correspond to just 2.5% of the distribution on either side. All right, so here's how I could do that in R. For the lower bound, I would take my observed beta hat 1 and subtract that t-star critical value times 0.1552. And for the upper bound, I would take that beta 1 and add the t-star value times the standard error, 0.1552. And this t-star value, it's going to be something close to 2. That's about what the critical value is. And as my sample size grows, it would get closer and closer to 1.96, which is what it would be under a normal distribution. Okay, so those are the confidence intervals we've talked about so far. But it turns out there are two other intervals that quantify uncertainty that we might want to calculate. So these confidence intervals, the ones we've calculated so far, are useful if we're trying to estimate variability or we're trying to estimate inference. If we're interested in inference, and that is describing the relationship between x and y. But often we're interested in predicting values for observations, and under those circumstances, we might want intervals for those predictions, and so that's what we're going to talk about today. So the first kind of confidence interval is the confidence interval for the mean response in y for a given x value. And so what that means is for a given, like for example, in the leaf length and leaf width example, if I wanted to know what is the average length of a leaf that has a width of 5 centimeters. My x star here is 5 centimeters, and my mean response would be that average length for a leaf of that value. So that would be a confidence interval for the mean response in y given a particular x star value. The other type of interval would be the confidence interval for an individual response y for a given x star value, and that's a little bit different. So that would be like if I had a particular leaf that was 5 centimeters and I wanted to guess how long that leaf was without measuring it, and I wanted an uncertainty interval for that particular leaf. That would be a confidence interval for an individual response y. So the difference between these two, they both are going to have the same x star value. So for a given for a given observed x value, so for a given like leaf width, for example. But the first one I'm saying for a leaf that's 5 centimeters wide, on average, how long is that leaf? And the second one is saying for a particular leaf that's 5 centimeters wide, how long is that particular leaf? So the estimate for both of these is going to be the same, but the confidence interval is going to be different because the uncertainty is different depending on if we're trying to say something about an average or an individual. So why are these different? Which do you think is easier to estimate, the average response or an individual response? I have the answer here, so you also could just read it on the slide. So it's going to be harder to predict a single response, like a particular leaf's length, versus saying on average how long leaves will be with a certain width. And so if I'm saying that it's basically harder to predict the individual response, what do you think that means in terms of the standard error, in terms of the uncertainty? Which one do you think would have a bigger standard error, the one that I'm trying to estimate an average response or an individual response? Exactly, the individual is going to have a bigger standard error, and that's because it's harder to say something about just a single leaf, and so there's going to be more uncertainty in that estimate. So the standard error of the prediction interval, which is this interval for an individual response, is going to be larger. So this is what those confidence intervals look like. There's two different types. The confidence interval for mu y, this is the confidence interval for the mean response y. And then the prediction interval is another way of saying the confidence interval for the individual response in y. So both of them have the same center, the same predicted value, which is just going to be y hat. It's the predicted y for a given x. What's the equation for y hat that I would use if I were trying to plug that in for a given x star? If you had some model output that included beta hat 0 and beta hat 1, how could you use that to get y hat? Exactly. I could take beta hat 0 plus beta hat 1x, and that will give me y hat. So that'll be the same for both of these intervals. The t statistic is going to be the critical value for the tn minus 2 distribution, so that will be the same for both. But then the standard error is going to take two different values depending on which interval you're interested in. And so it's going to be the standard error for mu hat for the confidence interval for a mean response of y, and the standard error for y hat for the prediction interval or the confidence interval for an individual response of y. And so which of these will be larger based on what we were just talking about before, about which one's easier to estimate? Exactly, the y hat one will be larger since it's a little bit harder to estimate something for an individual than it is for an average. So these are the equations for the two standard errors. What's the difference between these two equations? Yeah, this one here. And so that's what makes this one bigger. It's got this extra 1 in the square root. And that's just because basically an individual response is going to vary from the mean on average with a standard deviation of sigma epsilon. So this is equivalent to, if you could pull this sigma hat like through, and you would get the sigma hat epsilon plus sigma hat epsilon times 1 over n plus this quantity here. So basically this is going to be bigger by that sigma hat epsilon amount. So that quantifies how much bigger the estimated standard error is for an individual response as opposed to an average response. Okay, so to do this in R, we can use the predict function. And by default, when you use the predict function, it gives you, if you use it just like this, where you put the model object as the only argument inside the predict function, the output is going to be the predicted values for the observations in the data frame. So by default, the predict function gives you exactly the same output as the fitted function when you just use it like this. So for example, the first observation in the Magnolia data set was predicted to have a leaf length of 14.07. The second, based on its leaf width, was predicted to be 15.7, and the third was 15.43. You can pass it a new data set, which is mostly what we would be doing when we're trying to predict something. But just to show you kind of how these will compare, we'll first do this where we calculate these confidence intervals and prediction intervals for the observed data, and then we'll create a new data set. So if you want to calculate the confidence interval for the mean response, you would set interval equals confidence, and it will give you this output here. So again, the first observation in a Magnolia dataset based on the leaf width has a predicted length of 14.0732 with a lower bound of 12.62 and an upper bound of 15.5. So what this is telling me is that the first observation in my dataset, based on its leaf width, I'm saying that on average, we expect leaves of that width to have an average length of 14.07, and this is the confidence interval for that average. I can also do the prediction intervals, which again are going to be wider. In R, if you try to calculate prediction intervals on your actual data, so without passing it new data, you'll get this warning that says predictions on current data refer to future responses. And that's because the prediction intervals are intended to be for a future observation, individual observation. That's why you're adding in a little bit more variability there. And so what this is telling me is that if I were to see a new leaf with the same width as this first one, I would guess that its length was 14.07 for that particular leaf, and my confidence interval would be from 3.4 to 24.7. And so you'll notice that this confidence interval, which is a confidence interval for the individual response, also known as a prediction interval, is much wider than this confidence interval. Both of the predictions are the same, but the confidence interval is much wider in the second case because I'm trying to build a prediction for an individual as opposed to an average response. More often when we're using prediction intervals, it's going to be because we have some new data. And so I can create like a new data set in R that includes new observations. And so let's say I went out into the MagQuad and I found 3 leaves and I measured their widths, but I didn't want to measure their lengths. And so these 3 leaves had a width of 5 centimeters, 7.2 centimeters, and 4.3 centimeters. I could make a new data frame with those values. And I'd want to be careful to make sure that the values I put in my new data frame were using the same units as the ones of my model. And I also would make sure that the column of my new data frame exactly matched the name of the column from my model. So I've got this new data frame with 1 column, leaf width, and 3 rows. And I can use the predict function where, again, the first argument is that model that we just fit. But now I'm passing it some new data. I'm passing it this new Magnolia data. And I'm saying I would like a prediction interval for this new data. And so this is saying that a leaf with a width of 5 centimeters is going to have, I'm predicting the length will be 14.02 centimeters, and this is my confidence interval for that prediction. And similarly, if I saw a new leaf with 7.2 centimeters wide, I'm going to guess that the length is 14.9 centimeters, and this would be my confidence interval for that prediction. All right, so go back into that application exercise, and we have 2 different questions here. The first one, you're interested in the predicted Porsche price For cars that have 50,000 miles previously driven, you're interested in the predicted price on average. So you want the average predicted price. Calculate this value with an appropriate confidence interval. So the confidence interval for the mean response. And then the second prompt, you're interested in the predicted price for a particular Porsche, so an individual with 40,000 miles previously driven. Calculate this value in an appropriate confidence interval. And so I'll give you a couple minutes to do that, and then we will do it together. Okay, if I wanted to make a new data set that included a Porsche with 50,000 miles previously driven, what could I do to do that? What function could I use to create a new data frame? No. Yeah, data frame. And I'm going to call my column the same thing as the column that I am interested in for my model. So I'll call it mileage. And I need that to exactly match what I used in my model in order for the predict function to be able to plug in this new value. And so if I wanted to build a prediction for cars that had 50,000 miles, what would I put in for this? Yeah, it'd be 50.0, and that's going to be because this data set is in thousands, and so I want to make sure that this is in the same units as my original data. Very good. So I'm going to run that, and now I have this new data frame. It just has one observation for the observation I'm interested in predicting. And so then if I wanted to get that prediction from my model, what function would I use? Predict, yep. And what would the first argument be? Mod. And then how would I put in my new data? Yeah, new data equals new data. And then if I wanted this, in this first one, I was interested in a predicted value for the average price for a car that has 50,000 miles. And so what would I use for my interval for that? I think someone said it. Confidence, yeah. And so what this tells me is that if I had a car or many cars with 50,000 miles, on average, I would expect them to cost about $41,000, $41,620, with a confidence interval, a 95% confidence interval from 38,000 to 44,000. Yes?
What's the difference if we put predict instead of confidence?
If you do prediction instead, so that's gonna. If you do prediction, it's gonna be those prediction intervals for the individual response. And so what that means, the difference between these two, we can here. Let me render it so you can see them side by side. So the confidence interval goes from 38.4 to 44.8. This is the confidence interval for the mean response. The prediction interval goes from 26.5 to 56.6. That's the prediction interval for the individual response. So the difference in interpretation, you'll notice the fitted value is exactly the same. That's just the prediction, but the confidence interval is different. And that's because the interpretation of this first one is that if you had several cars with 50,000 miles on them, we'd expect on average that they would have a predicted price of $41,620. And so this is a confidence interval for that average. Versus if we had a single, just one car with 50,000 miles, and we were trying to guess how much that car cost, we would guess that it also cost $41,620. But because we're just predicting a single individual's car, we've got more uncertainty. So the interval for that prediction is from 26,000 to 56,000. Okay, yeah. Does that make sense?
Yeah.
Nice. So now we're gonna do that. You've preempted the next part. So we're gonna change. New data is gonna be. Now we're going to look at 40,000 miles. So we had an individual car with 40,000 miles on it. And so if I wanted to make a prediction interval for that single car, I could plug in that new data that has that 40 in it. And now what kind of interval would I use if I was interested in an individual response? Prediction, yeah. And so now I would predict that it would have, it would be $47,500, and the interval goes from 32,572 to 62,456. Are there any questions about that? So the nice thing with these is that you can, so far we just had two values, but you could have a whole data set with several values. For example, I could have, let's say I had 100 new cars that I was interested in getting the prediction values for. My new data set now has 100 observations with these new mileage for each of those, and I could get the predicted values along with their confidence intervals for all 100 of those observations by plugging that new data in. So this is nice because if we're interested in a prediction model, this allows us to sort of get intervals for those. All right. So if there's no other questions, then I'm going to switch to doing this whole game where we can start kind of walking through the whole process kind of end to end if I were to be doing a data analysis. And so for that, I'm going to just pull, this is just some Magnolia data that I grabbed earlier. I'm going to make a new fresh file so we can start from scratch here. Oops. Oh dear. I'm going to save this. All right, let's stick this data in. Okay, so my first little R chunk is going to just be to load my packages and data. And so all this is just this Magnolia data that I've sampled from that from that data set, from that application. I'm going to click this render on save, and so that means every time I save my file, it will render it for me. And then I'm also going to go ahead and render it so that I make sure that I am saving it and also checking out that HTML file each time to make sure that there are no mistakes that I've missed. So I can get rid of this output. This is just a message that gets printed by default by the tidyverse package. I can hide that by adding some little options up here to this R chunk. So I can add this message false, warning false to get rid of that. And the other thing I can do is I might not be interested in printing out this whole data set that I've just read in. So if I wanted to suppress this little chunk of R code so that it would still run, but you wouldn't actually see it in the HTML file, I can add this echo false option. And so echo, when echo is true, it will show your R chunks, which is the default. When it's false, it'll hide them. And so now I don't see it, although it is still running in the background. Okay, so if I were doing this for real, I would first load in my data, and then I might have a little section. So I'm going to make a little header here called Exploratory Analysis. And in this section, this is going to be where I'm looking at my data. I'm examining whether there are any missing values. I'm seeing how many rows there are in my data frame. And I'm describing what it is ultimately that I'm trying to, what kind of question I'm trying to answer. So I'll write something like, I am interested in the relationship between leaf length and leaf width. My data consists of, and I can use, so in R, if you use this backtick R, it allows you to put R code in line that then will run for you. So instead of having to count up the number of rows, I can just use this nRow function with that R to let R know that I would like for it to run the number of rows on this data frame. So I can do nRow Magnolia data. So my data consists of nRow Magnolia data observations and two variables. There is no missing data. Each observation represents one magnolia leaf with the length and width measured in centimeters. So just to check off what I've done so far, I've described what I'm going to be looking at. I've described how many rows are in my data and how many columns. I've indicated that there's no missing data. If there was some, I would say so. And I've said what each observation represents, which in this case is one magnolia leaf with a length and width measured. So what I've kind of done here is in your labs, the first question has often been something like this, and so that's sort of trying to emulate what you should be doing when you're starting an analysis. So if I render this document, you'll see instead of it saying this R nRow Magnolia data, it now says the actual number, 78 observations. Okay, so if I'm interested in the relationship between leaf length and leaf width and I'm doing an exploratory data analysis, how might I visualize that to see kind of what the relationship looks like before I fit any models? What kind of plot could I make? A scatter plot, exactly. So if I'm making a scatter plot, my data is going to be that magnolia data. If I'm interested in predicting leaf length from leaf width, which would I put on my x-axis? Width, exactly. On my y-axis, I'll put length. And then if I want to make a scatter plot, what geom would I use? Exactly, geom point. And so this is almost done. To make this kind of publication worthy, I would want to make sure that I update the labels here so that instead of being variable names, they're actual text. So I'm going to change this to leaf width in centimeters. And I'll change the y-axis to leaf length in centimeters. All right, so looking at this, it looks like there's maybe a bit of a positive relationship, although there's kind of a lot of variability. It doesn't look like there's a nonlinear relationship, so I can probably proceed with fitting a simple linear regression model. And so my next step is going to be modeling the relationship. And so I might add some text to say something like, we are interested in how leaf width predicts leaf length in magnolia leaves. To estimate this, we will fit a simple linear regression model. So if I want to do that, what function would I use? LM, that's right. And what would my Y leaf length? Yes. Leaf width. And the data will be magnolia data. So there's my model. Now before I start interpreting my model, I'm first going to assess the conditions. So I'm going to make a little subheader here that says assess the conditions of the linear model. And so what are the conditions for simple linear regression? Linearity. Constant variance, yeah. What other assumptions are there for simple linear regression? Bless you. Does anyone know another assumption we need to make? We have zero mean. There's three more. What assumption was violated by when we were doing our sampling outside when you did it yourself instead of using my little app? Randomness, and there's another one that was violated by that as well. Independence, that's right. And then there's one more assumption, has to do with the error term, with its distribution. Yep, normally distributed errors. Great, so those are the 6 assumptions. So if we wanted to test, there's one plot we could use. Well, first of all, zero mean is just true by default. So zero mean of the residuals. Zero mean is true by default since we are using simple linear regression via least squares. Randomness and independence are assumed based on our sampling techniques. So for this data, I got these values by using my random sampler app, which randomly measured leaves on the quad, allegedly. So So that is good. So we've got just the three more assumptions to test. What is a plot that can assess both linearity and constant variance? Residuals versus Spitz, exactly. So to test the linearity, or to assess the linearity and constant variance assumptions, we will use a residuals versus Spitz plot. And what kind of plot can you use to examine how the residuals are distributed? Do you remember what kind of plot we used when we were checking that normality assumption? A histogram, yep, we can use a histogram. And we also used a QQ plot, so we can use both of those. The QQ are those quantile plots. Great, okay, so now let's do that. So first, we're going to do our residuals versus Spitz plot. And so to do that, I need to add the residuals as well as the fitted values to my data frame. What function can I use to add variables to a data frame? Mutate, yep. And if I want to add the residuals, what can I do for that? Residuals. And what if I want to add the fitted values? I think somebody said it. What is it? Fitted? Were you saying it was something minus?
Yeah, I forgot. Like something minus.
Yes, so y hat here is going to be equal to the fitted. The residuals, I can use this residuals function, or alternatively, so there's two different ways to calculate the residuals. I also could do like the y minus y hat to get those. And these two will get me the same answer. Okay, so now that I've done this, my residuals and my fit, oh, I need to run my model. Let me make sure, I called it model, not mod. There we go, so I'm gonna go ahead and render this to make sure that it is updating. Okay, so now I've got my y hat values and my residuals in here, and so for my residuals versus Spitz plot, I'm going to put the fitted values on the x-axis and the residuals on the y-axis. If I wanted to add a line at 0, how could I do that? A horizontal line? Yeah, geom h line. And I'll set the y-intercept equal to 0. This is my residuals versus Spitz plot. I'm going to do one more thing. I'm just going to add some labels here. So the x-axis is going to be the fitted values, and the y-axis is going to be the residuals. All right, so this is checking for linearity and constant variance. How do you think that this looks? It looks pretty good to me. Basically, you're kind of looking on either side of the 0. You want to have basically like random points on either side. You don't want to see any strong patterns that would suggest nonlinearity. And for constant variance, you basically want the band, like the width of the points, to be essentially even as you go down or across the x-axis. And so there's not really an obvious like fan shape or something where it looks like there's a lot more variability in one part than another. So looking at this, it looks pretty good to me. I don't feel too concerned. This seems, I feel pretty confident in that those assumptions are fine with this particular model. And then the next one is going to be that QQ plot. And so for that, we're going to use, in the aesthetic part, we're going to say sample equals E. That's going to make the residuals be the thing that we're doing this QQ plot on. And then what geom do I use for the QQ plot? Going to be geom QQ, and then for a reference line I can use geom QQ line. And so looking at these, I basically want these points to essentially fall along this line, which they do pretty well to indicate that the residuals are pretty normally distributed. So this looks pretty good to me. The last thing I could do if I wanted to look, another way to look at the distribution of the residuals would be to look at a histogram of those residuals. And so I can do that as well. And those look pretty normal. I might make the number of bins a little bit smaller here. That looks pretty normally distributed, so that I feel pretty good about that. So then down beneath this, I'm going to add a line here that states the residuals versus Spitz plot indicates that the linearity and constant variance assumptions are not violated. The QQ plot and histogram of the residuals indicates the normality assumption is not violated. All right, so now that we've checked the assumptions, we can actually interpret our results. And so now I can print a summary of my model. And if I come over here, we can look at the rendered version of my full report. I can come down to the summary, and I can pull out the pieces that I'm interested in. And so in this particular case, perhaps I'm interested in the beta hat one here, this 34.2. And so what I might do is add a line here that says for every 1 centimeter increase in leaf width, we expect leaf length to increase by 0.342 centimeters. And then to close things off, I would include a 95% confidence interval of that effect. All right, so hopefully this has been kind of helpful to sort of tie in what we've done so far. On Tuesday, you will have a lab. Well, you'll get a chance to sort of do the same thing, and then we'll have a review on Thursday.